Hey guys, welcome back, I'm Jay. In this episode, we're going to look at the AWS Data Warehouse Solution, Amazon Redshift. Amazon Redshift is an enterprise-level, petabyte-scale, fully managed data warehouse solution for online analytical processing. So why do you need a petabyte-scale data warehouse? Imagine you have an online shopping site that serves hundreds of thousands of customers. You can analyze popular products across millions of products, and summarize the most popular products of all time, as well as on a weekly and monthly basis in each category. You need to navigate across millions of records and query many tables. Traditional databases are not optimized for complex queries on very large datasets. You need an enterprise-level data warehouse for this. Redshift makes it simple and cost-effective to analyze all your data, using standard SQL and your existing BI tools. It allows you to run complex analytic queries against terabytes to petabytes of structured data, using sophisticated query optimization, columnar store on high-performance storage, and massively parallel query execution. Redshift is an RDBMS that supports standard SQL queries. It's built from PostgreSQL but designed for OLAP applications. The core infrastructure component of a Redshift data warehouse is a cluster. A cluster is composed of a leader node and one or more compute nodes. Redshift uses the columnar storage, where each data block stores values of a single column for multiple rows. Columnar storage drastically reduces the disk I/O requirements, and the amount of data loaded from the disk. Redshift is optimized for high-performance analysis and reporting of very large datasets. Redshift is integrated with many AWS services, such as Data Lake using Amazon S3, and Business Intelligence using Amazon QuickSight. For example, you can use Redshift Spectrum directly to query massive data stored in S3. You can connect QuickSight to Redshift and quickly build business insights. The core infrastructure component of a Redshift data warehouse is a cluster. A cluster can contain from 1 to 128 compute nodes. If a cluster has multiple compute nodes, you need an additional leader node to coordinate the compute nodes and handle external communication. Your client application interacts directly only with the leader node. The leader node manages communications with client applications and all communication with compute nodes. Redshift communicates with client applications using standard JDBC and ODBC drivers for PostgreSQL. The leader node parses execution plans to carry out database operations. The execution plan contains a series of steps necessary to obtain results for complex queries. Based on the execution plan, the leader node compiles code, distributes the compiled code to the compute nodes, and assigns a portion of the data to each compute node. The compute nodes execute the compiled code, and send intermediate results back to the leader node for final aggregation. The compute nodes are in private network space, you can't access compute nodes directly. Each compute node has its own dedicated CPU, memory, and attached disk storage, which is determined by the node type. Each compute node is partitioned into slices, and each slice is allocated a portion of node's memory and disk space, and processes a portion of the workload assigned to the node. The leader node manages the distribution of data and workloads to the slices, and the slices work in parallel to complete the operation. Redshift offers different node types to suit your workloads. These node types are EC2 instances with different compute capacities, memories, and storage sizes optimized for Redshift workloads. You can choose the number of nodes based on the data size and performance requirements. As your data grows, you can add more compute nodes to increase the storage size of the cluster. Dense compute or DC2 nodes allow you to create compute-intensive data warehouses. DC2 nodes store your data locally using SSD storage for high performance. AWS recommends DC2 nodes for uncompressed datasets under 1 TB, for the best performance at the lowest price. DC2 nodes offer two options, DC2 Large and DC2 8x Large. Each DC2 Large has 2 vCPU, 15 GB memory, 160 GB SSD storage, and supports 0.6 GB I/O per second. Each DC2 8x Large has 32 vCPU, 244 GB memory, 2.56 TB SSD storage, and supports 7.5 GB I/O per second. Dense storage or DS2 nodes allow you to create large data warehouses using hard disk drive. For new data warehouses, AWS recommends using RA3 nodes instead of DS2, to get more storage and better performance for the same on-demand cost. DS2 nodes offer two options, DS2 Extra Large and DS2 8x Large. Each DS2 Extra Large has 4 vCPU, 31 GB memory, 2 TB HDD storage, and supports 0.4 GB I/O per second. Each DS28X large comes with 36 vCPU, 244 GB memory, 16 TB HDD storage, and supports 3.3 GB I/O per second. RA3 nodes offer Redshift managed storage that allows you to create performance-optimized data warehouses and scale compute and storage independently. With RA3, you can choose the number of nodes based on the performance requirements, and only pay for the managed storage that you use. Redshift Managed Storage or RMS uses large high-performance SSDs in each RA3 node for fast local storage, and S3 for longer-term durable storage. If the data in a node grows beyond the size of the large local SSDs, RMS automatically offloads that data to S3. RA3 nodes offer two options, RA3 4X large and RA3 16X large nodes. Each RA3 4X large node comes with 12 vCPU, 96 GB memory, up to 64 TB RMS storage, and supports 2 GB I/O per second. Each RA3 16X large node comes with 48 vCPU, 384 GB memory, up to 64 TB RMS storage, and supports 8 GB I/O per second. Redshift takes advantage of massively parallel processing or MPP by spreading workloads across multiple nodes. MPP enables fast execution of the most complex queries operating on large amounts of data. Redshift uses Columnar Storage to store database tables. When records enter the system, Redshift transparently converts the data to Columnar Storage for each of the columns. Storing data in a columnar fashion reduces the overall disk I/O requests, and uses less memory when executing queries. Data compression reduces the data size when it's stored, and reduces disk I/O when it's read from the storage. Redshift applies adaptive compression encoding for each column based on the column data type. When you execute a query, the compressed data is read into memory, then uncompressed during query execution. Loading less data into memory enables Redshift to allocate more memory to analyzing the data. Redshift Query Execution Engine incorporates a query optimizer that is MPP aware, and takes advantage of the columnar storage. The query optimizer implements significant enhancements for processing complex analytic queries, including multi-table joins, subqueries, and aggregation. Redshift caches the results of certain types of queries in memory on the leader node, to reduce query execution time and improve performance. When a user submits a query, Redshift checks the cache for a valid copy of the query results. If a match is found in the result cache, Redshift returns the cached results without executing the query. Redshift compiles complex queries and distributes fully optimized compiled code across all of the nodes of a cluster. Compiling queries eliminates the overhead associated with an interpreter and increases the execution speed. The compiled code is cached and shared across sessions. Subsequent executions of the same query will be faster. OLTP stands for Online Transactional Processing. OLTP databases are used for transactional processes where frequent reads and writes are required. Applications use OLTP databases to support day-to-day business operations. OLTP databases allow users and applications to perform fast and frequent operations on fewer data. Most data stored in OLTP databases are current data, where data are frequently updated and new records are constantly inserted. Most OLTP databases have row-oriented data store architectures, optimized for multiple concurrent operations. OLTP databases are widely used for e-commerce applications, web apps, and gaming applications. For example, you have an online shopping website. You can use an OLTP database to store products, orders, and customer information. Operations like adding new products, updating customer information, processing orders are online transactional processes. These operations are performed frequently on a small amount of data. OLAP stands for Online Analytical Processing. OLAP databases are used for analytical processes, where heavy data read across multiple tables or data stores are required. Data warehouse is a typical OLAP database. Data warehouse is commonly used to support data mining, data analysis, business summary and reporting, and business intelligence. Data warehouse allows users to run large queries on massive data across multiple tables or data stores. These queries are complex and slow to run, and you don't need to respond to the result in real time. Data in data warehouse are historical and not updated very frequently, as your applications don't write data to data warehouse directly. Data are usually extracted and transformed before loading into the data warehouse. Most OLAP databases have column-oriented data store architectures that are optimized for multidimensional data queries, where you need to aggregate information of many columns from different tables or data stores. For example, you might want to extract sales information for different departments and summarize them in the same report. You might use business intelligence software to analyze the buying patterns between your customer groups and popular products. Columnar storage for database tables is an important factor in optimizing analytic query performance. It drastically reduces the overall disk I/O requirements and the amount of data you need to load from disk. In a typical RDBMS table, each row contains field values for a single record. The row-wise storage stores each row of records in a data block. Because the size of a row varies. If the block size is smaller than the row size, storage for an entire row may take more than one block. If the block size is larger than the row size, storage for an entire row may take less than one block, resulting in inefficient use of disk space. In OLTP applications, most transactions involve frequently reading and writing a small number of records, containing all of the values for the entire row. As a result, row-wise storage is optimal for OLTP databases. In OLAP applications, most queries read large amounts of records with complex column joins. You need a columnar storage to perform efficient reads. The columnar storage stores each column of values from multiple records in a data block. Using columnar storage, each data block holds much more data than row-based storage. Reading the same number of column field values for the same number of records requires much less I/O operations compared to row-wise storage. In addition, because each block holds the same type of data, block data can use a compression scheme specific for the column data type, further reducing disk space and I/O. As a result, retrieving data for the same number of rows from the columnar storage requires much less I/O operations and uses less memory than row-wise storage. Redshift provides commands that make it easy to move large amounts of data into Redshift from other data stores. You can use copy command to load data from Amazon S3, DynamoDB, EMR, and remote hosts such as EC2 instances. Alternatively, you can use insert command to add data to a table. However, the copy command is the most efficient way to load a table. The copy command leverages the Redshift MPP architecture to read and load data in parallel. It's much more efficient than insert. If your data files are encrypted in S3, the copy command decrypts the data as it performs the load. If your files are compressed using gzip, lzop, or bzip2, copy command can speed up the load process by uncompressing the files as they are read. If you update or delete a significant amount of data after your initial data load, you should run a vacuum command to reorganize your data and reclaim space after deletes, and run an analyze command to update table statistics. To unload data from Redshift to a set of files in S3, you can use the unload command with a select statement. For example, you can unload data as CSV files in either delimited format or fixed width format. You can also specify whether to compress the CSV files using gzip. Compression in Redshift is the column-level operation. Each column can have a different compression encoding. A compression encoding specifies the type of compression that is applied to a column, as new records are added to a table. You can apply compression encodings to columns in tables manually when you create the table, based on your own evaluation of the data. To apply compression manually, you specify compression encodings for individual columns, using the encode keyword in the create table statement. Alternatively, you can use automatic compression when you create and load a brand new table, using the copy command with comp update set to on. The copy command performs a compression analysis, and apply compression automatically based on sample data. You can also perform a compression analysis, without loading data or changing the compression on a table, by running the analyze compression command on an already populated table. You cannot change the compression encoding for a column, after the table is created. However, when you add a new column to the table using the alter table command, you can specify the encoding for the column. Redshift offers two types of backups, automated snapshots and manual snapshots. By default, Redshift enables automated backups of your cluster with 1-day retention period. You can configure it up to 35 days. If you set the retention period to 0, it will disable the automated backups. However, it's not recommended. You can also take a manual snapshot at any time. By default, manual snapshots are retained indefinitely, even after you delete your cluster. You can specify the retention period when you create a manual snapshot, or you can change the retention period by modifying the snapshot. You can configure Redshift to automatically copy your snapshots to another AWS region for disaster recovery. A snapshot contains data from any databases that are running on your cluster. It also contains information about your cluster, including the number of nodes, node type, and master username. You can restore your cluster from a snapshot. Redshift uses the cluster information to create a new cluster, and restores all the databases from the snapshot data. If a node fails in your Redshift cluster, Redshift will automatically detect and replace the failed node. In the event of a node failure, the cluster will be unavailable for queries and updates, until a replacement node is provisioned and added to the cluster. In a multi-node cluster, as soon as the replacement node is provisioned, data is replicated to the new node from other nodes in the same cluster. Single-node clusters do not support data replication. In a single-node cluster, you will need to restore the node from the snapshot. Redshift will restore your most frequently accessed data first, so that you can resume queries as quickly as possible. AWS recommends using at least 2 nodes for production. Redshift only supports single AZ deployments for a cluster, which means all your nodes in the cluster are deployed in one availability zone. If the entire availability zone of your Redshift cluster becomes unavailable, you won't be able to use your cluster until the AZ is recovered. To quickly recover from an AZ outage, you can restore your Redshift cluster in a new AZ from the snapshot. Redshift Spectrum is a feature of Redshift that enables you to run queries against exabytes of structured and unstructured data in S3, without loading the data into Redshift tables. Redshift Spectrum resides on dedicated servers that are independent of your Redshift cluster. It can scale out to thousands of instances to take advantage of massively parallel processing. To use Redshift Spectrum, you need to create Redshift Spectrum tables by defining the data structure for your files, and registering them as tables in an external data catalog, such as AWS Glue Data Catalog. After your Redshift Spectrum tables have been defined, you can query and join these tables as you do with normal Redshift tables. You can only query the data from the S3 bucket that is in the same AWS region as your Redshift cluster. Redshift Spectrum lets you separate storage and compute, allowing you to scale each independently. With Redshift Spectrum, you pay per terabyte of data scanned in addition to the Redshift cluster. In this episode, we've learned Amazon Redshift. Redshift is an enterprise-level, petabyte-scale, fully managed data warehousing service for online analytical processing. Redshift makes it simple and cost-effective to analyze all your data using standard SQL and your existing BI tools. Redshift is integrated with many AWS services, such as Data Lake using S3, and Business Intelligence using QuickSight. Redshift is a high-performance data warehouse platform that takes advantage of MPP by spreading workloads across multiple nodes. Redshift uses Columnar Storage to store database tables, which reduces the overall disk I/O requests and uses less memory when executing queries. Redshift applies adaptive compression encoding for each column based on the column data type. Redshift Query Execution Engine incorporates a query optimizer that is MPP aware, and takes advantage of the Columnar Storage. Redshift caches the results of certain types of queries in memory on the leader node, to reduce query execution time and improve performance. Redshift compiles complex queries and distributes fully optimized compiled code across all of the nodes of a cluster, which eliminates the overhead associated with an interpreter and increases the execution speed. Redshift Spectrum is a feature of Redshift that enables you to run queries against exabytes of data in S3, without loading the data into Redshift tables. The core infrastructure component of a Redshift data warehouse is a cluster. A cluster can contain from 1 to 128 compute nodes. If a cluster is provisioned with more than one compute node, an additional leader node coordinates the compute nodes and handles external communication. The leader node manages communications with client applications, and all communication with compute nodes. It parses execution plans to carry out database operations. Based on the execution plan, the leader node compiles code, distributes the compiled code to the compute nodes, and assigns a portion of the data to each compute node. The compute nodes execute the compiled code, and send intermediate results back to the leader node for final aggregation. Each compute node is partitioned into slices. Each slice is allocated a portion of the node's memory and disk space. The leader node manages the distribution of data and workloads to the slices. The slices work in parallel to complete the operation. Redshift offers different node types to accommodate your workloads. Dense compute nodes allow you to create compute-intensive data warehouses with local SSD storage. Dense storage nodes allow you to create large data warehouses using HDDs. AWS recommends using RA3 nodes instead. RA3 nodes come with Redshift Managed Storage, which allows you to create performance-optimized data warehouses and scale compute and storage independently. Redshift provides commands that make it easy to move large amounts of data into Redshift from other data stores. You can use copy command to load data from Amazon S3, DynamoDB, EMR, and remote hosts such as EC2 instances. To unload data from Redshift to a set of files in S3, you can use the unload command with a select statement. Redshift offers two backup options, automated snapshots and manual snapshots. By default, Redshift enables automated backups of your cluster with 1-day retention period. You can configure it up to 35 days. You can also take a manual snapshot at any time. By default, manual snapshots are retained indefinitely, even after you delete your cluster. You can configure Redshift to automatically copy your snapshots to another AWS region for disaster recovery. If a node fails in your Redshift cluster, Redshift will automatically detect and replace the failed node. In a multi-node cluster, Redshift data is replicated to the new node from other nodes in the same cluster. In a single node cluster, you will need to restore the node from the snapshot. AWS recommends using at least 2 nodes for production. Redshift only supports single AZ deployments for a cluster. In the event of an AZ outage, your Redshift cluster becomes unavailable. To quickly recover from an AZ outage, you can restore your Redshift cluster in a new AZ from the snapshot. Okay, that's all for Amazon Redshift. Thanks for watching and see you in the next episode.
Hope you've enjoyed watching this episode. If you liked the video, please help us and hit the like button. If you want to watch more tutorials, please subscribe to the Cloudemy TV channel. Make sure to turn on the notification and stay tuned. At Cloudemy, we're passionate about cloud and AI technology. Please share your feedback and thoughts in the comments below. Feel free to let us know what topics you'd like to watch. Happy watching and happy learning.